Now think of a situation where, let's say, suppose I had to model, an XOR gate, right, the functioning of an XOR or XOR, right. Now for an XOR, right, what do you have? I mean, let's say, suppose I go back to this example x1 x2 y. What is the XOR thing? 0 0 0, I thought, right. 0 0 is 0, 0 1 is 1, 1 0 is 1, and 1 1 is 0, right. This is the XOR, right. Now if you again plot it, okay, the same way, okay, as we did before. Now suppose I say that, right, my 0 0 I am going to indicate with a 0 because the output label is a 0. Then 0 1, right, is somewhere here, which I will indicate with a cross because my label for that input is 1. Okay, so this is x1 again, okay, this is x2. Oh, sorry, okay, 0 1 is here, okay, 0 1 is here. Okay, so this is 0 1, this guy is 1 0, and 0 1 and 1 0 I am going to indicate by a cross because the label for that is 1, right. So I am going to indicate this as 1 and this is 1 0. So also has a value 1, and then 1 1, right, is out here, and that I am going to indicate by a circle because the output corresponding to that, the output label is 0. So now, right, if you ask with and of course, right, I mean, remember that that an extension to a higher dimension, for example, right, from on a 2D plane, it looks like a line will do the separation. On a higher, this one it will be a hyperplane, and so on, right. So this is the simplest that you can illustrate, right, on this one. Now if you think about this, right, I mean, whichever way you try to draw a line, right, I mean, you won't be able to do a classification, right, because suppose I try, right, drawing a line, okay, suppose I try drawing a line like that, then again I am not able to classify because right, along with this guy there is another label which is, right, two kind of different labels are coming in on this side. Suppose I draw like this, then again there is a problem because on this side there is again a confusion. If I go there, then again there is a confusion because there is one label out there. So whichever way you try, right, whatever you try, I mean, try like that, whichever way you try, right, with a single line, you won't be able to solve this, right. And that's where I think, that's where people sort of got a little whatever, right. I mean, they kind of understood that, right, this is not so great. And okay, right, this you can also show that, right, this is a condition that you cannot satisfy in any case. So if you just go back and try to do the same thing, okay, which we did before, just write down the conditions, right. What do you have? So let's say W1 0 plus W2 0. What will you say? Yes, less than theta, right? This is what you want. Then you have W1 0 plus W2 1 is greater than or equal to theta. Then you will say W1 1. Okay, in reality, right, one does not solve it like this, okay. There is something called a perceptron learning rule, but for the time being, right, we will just do it brute force. So W1 into 1 plus W2 into 0, this will be greater than or equal to theta, and then W1 1 plus W2 into 1 will be less than theta, right. This is how you want the labels to be. Now, which means that theta is of course greater than 0 from the first condition. The second one says that W2 should be, what is it, greater than or equal to theta, right. And then the third condition says that W1 should be greater than or equal to theta, but then the last condition says W1 plus W2 should be less than theta, right, and this you cannot satisfy, right, which means even that is also evident, I mean, which is a look at it graphically. So here is where, right, came sort of a lull period, right, for a perceptron, because people felt that, well, I mean, right, you can probably do only some things with it, right. And to sort of, right, go kind of further, right, I'll just introduce what is called a general form of a perceptron. Okay, this will just make the math a little more easy, I mean, in terms of matrix vector notations. So a general form of a perceptron. Okay, how does that look? So we again kind of go back to the same condition. Let's say that y is equal to 1 if summation wi xi, but right, note this index. Okay, I'm making it run from I equal to 1 to n greater than or equal to theta, 0 otherwise. Okay, and so what we can do is, right, this we can alternatively write it as summation wi xi I equal to 1 to n minus theta is actually greater than or equal to 0. Okay. Let us write down a vector w, right, to be this. Let us write this as w naught, w1, w2 all the way up to wn. So this w1 to w1 are the same weights, right, that were all sitting in that original summation. There is this w0 that I have additionally introduced, and then for x, right, I am going to write this as 1, okay, x naught, let me write it as x naught, x1, x2 all the way up to xn, where x1 to xn are again the inputs, and then x naught is something additional, right, which right we have introduced. Now if you really look at this expansion, right, so what you have is, suppose I wanted to write this, right, in terms of, so the idea is that, right, you want to be able to express this entire operation as W transpose, okay, x is actually greater than or equal to 0 for your y to be 1, and right, y is 0 otherwise, right. So you just, I mean, you don't want to kind of mess with this theta and all separately, right, you just want to right, put them all together. So now what should be your, I mean, right, if you want to rewrite, right, this, okay, this one in this form, okay, so what do you think should your W naught and x naught be? I mean, what should be W naught and what should be x naught? X naught is x naught is 1, right, I mean, okay, that's all, because see your W should become the unknown. Okay, always, I mean, right, you don't want to mix up. I mean, you might argue, can I not put you know, that is a theta under x naught, right? That's not the idea. The idea is that you want to keep the W as the unknown, right? It contains the bias and the weight, so right, that becomes your unknown vector, and then x will not have any unknowns. X naught will become 1. Okay, so if you think about it, this will become 1, and W naught will then be minus theta, right? So this W naught is actually equal to minus theta, which is what we call as a bias, right. So we can also call this as a simple term B, instead of trying to remember some minus theta and all that. Think of it as some quantity that is B, and right, what you are sort of, right, effectively saying is that solving this problem is equivalent to solving something like, right, a W transpose x greater than, I mean, find a W such that for that rule, right, that you have, for example, this x1 x2 y kind of rule, you should find this W which involves the bias as well as the weights, right. And this is going to be the case whatever be it, right, whether you have a million neurons connecting, you know, with each other and so on, except that there the scale will be much higher, right. You're going to look at millions of these weights and so on, and here, you know, it's at a very what do you call, no, at a very small scale, but the idea is still the same, right. You still have to compute these unknowns, the weights and the bias, okay, that will always be the case. And irrespective of whether you are solving a regression problem or you know, or right, whether you are doing a classification problem, doesn't really matter. Eventually it will all boil down to computer. What will be the loss function could change, right, depending upon whether you are doing a classification kind of a problem or whether you are going to do a regression kind of problem. Okay, now, right, what happened was then, right, then it was actually shown that okay, then, right, what followed was actually an interesting exercise, right, where they showed that instead of just having one neuron, right, and then of course, you know, being able to show that, right, you cannot use that to model as something like a nonlinear sort of a classification. If you think about it, with one line you are not able to do it, right. So they said, right, why don't you have, right, extra this one, right, I mean, why don't you introduce more number of neurons to solve the problem. But then how do you introduce them and where do you introduce them, right? That's where this notion of a hidden layer, right, came. Okay, so this notion, I mean, if you think about this, right, I mean, so these are the layers. So for example, right, when you say that you have a deep network, right, what you really mean is you've got several of these layers, right, you know, coming okay, in between. Now, so what was done was you again sort of have, so right, one of the simplest things, right, that you can do is, okay, you have the inputs again, okay, your x1 and x2. I'm going to solve the same XOR problem now, but now what has been done is, right, you have introduced an additional layer in between, so to say. Okay, what by layer I mean, right, this thing, right, which has come in between, and then again you have an output neuron. So earlier, right, I mean, you had these two inputs, you had this output neuron, right, that is the only thing you had. Now in between, okay, you've added a layer of again neurons. Now you can ask how many neurons you need and so on, but right now I'm just going to show that, right, with two neurons, okay, we should be able to solve this problem. And right, this kind of an uncertainty will always exist. I mean, for a given problem, how many layers do you need, how many neurons do you need effectively, and all, right, nobody knows. Okay, so that is why all these GPUs and all are needed, so that you can keep running them and then try to see which loss function fits the best, which architecture fits the best. So really there are no easy answers, but then you know, certain kind of what do you call this, the results are available that actually indicate what these things can do. Okay, and I will actually talk about them, right, as we go along. But for the time being, right, just kind of think about being able to again solve the XOR problem, but now, right, by actually introducing two more neurons in between. Okay, what we call is say additional layer, and you know, whenever somebody talks about a deep network with a certain number of layers, for example, this one we won't call it a 3-layer network, we'll call it a 2-layer network. because the hidden layer, see the layers are the places where there is a computation going on. See, x1, x2 is just an input, right? You're not really computing anything there, whereas in the middle one we will compute something. The output neuron will actually compute something. So in that sense, right, we'll call this as the input layer, this will be the hidden layer, this will be the output layer. Now you can have bunch of these, you don't need just one hidden layer, many a time you will have many hidden layers coming in between, and all that along with the output layer is what will sort of, right, tell you what is the kind of, right, depth of your this one network. So in this case, right, it has a depth of 2. It's got, you know, so it's got actually 2 layers, right, and those are the layers where there is a computation going on. Okay. Now let's just label things like, you know, so let's say that, right, here we've got theta 1, okay, for this. Let's say we got a, you know, theta 2 for this, and then we got a theta 3, and like I said, right, a neuron gets right, I mean, inputs from all the right previous things. So similarly, each neuron should get input, should get an should receive you know, input from all the right previous layers, and in this case it's just x1 and x2. So right, so basically this guy will get inputs from here, then this other neuron will also get inputs from x1 and x2, and similarly this neuron, right, will get an input from here as well as it will actually get an input from here, and then you have an y, and the y is still the same old XOR, right, that you had there. Okay, that is the one that you are still interested in. But now, right, what we will do is we will just follow a nomenclature. Okay, we will write this as we will call these weights now, as instead of calling W1, W2, we will call them as W11. That means from the first neuron or whatever. Let's call this as neuron number 1, neuron number 2, neuron number 3. So neuron number 1 to input 1, neuron number 1 to input 2. That will be W12. Okay, so that's this weight on this arm. Okay. And then you have like W21, okay, that will be the weight that gets applied to x1 when that goes as input to the now neuron number 2, and then this, let's call this as W22. Okay, I think this is just this one notation. And similarly, here we will call this as W31, okay, and this will call as W32, and then you have a theta 3 there. So if you kind of yeah, so for the same XOR, right? So this we are trying to solve the XOR problem, right, by introducing additional bunch of neurons there. Now I'm just going to write down these values, okay? A possible choice for the biases and weights. So the biases are theta 1, theta 2, theta 3, or minus of that. Okay, so let's not worry about minus and all that. Just say that there is a bias that will relate to this. You see theta sitting there. And there are the weights, which are all these, you know, interconnections, and you know, these things are called fully connected. If you see, right, this is called fully connected because you get, I mean, suppose I had x1 to xn instead of just 2 x1, if I had x1 to xn, they would all come in. So you can imagine, right, so you can imagine how many weights you eventually end up needing. So which is also the reason why later, right, we talk about a convolutional neural network and so on, because that has much less weights, just like your LTI sort of a system, right, where you can have local where you can have a convolution going on, right, which is like invariant, right. I mean, you don't change when you do an impulse response, right, when you apply it on a signal, you don't change it, right, as you go along the signal, it remains the same. Whereas here, right, you can think about this as being some weighted averaging that's actually changing, right, every time. So which means that it's computationally much more expensive, a lot of unknowns involved, but that's the way it evolved, right. Now, okay, now I'm just going to say that a possible choice, right, this is not unique, okay, a possible choice for the weights and the biases, a possible choice could be this. The biases is, I'm going to write this as W1. I mean, I'll just leave it to you to check this. Okay, W11 is 2, W21 is equal to -1, W12 is equal to -1, then W22 is equal to 2. Then the thetas, right? Theta 1 is 1.5. Like I said, right? These don't have to be binary valued or anything. Theta 2 is equal to 1.5, and theta 3 is equal to 1. And all this for still a Boolean sort of implementation, right? Now, okay. Now what? Okay. Now in this table, right? I'll just write down so x1, x2, and then summation. Let's say what is this? W1j xj. W1j xj, j equal to 1 to 2. Then I am going to write W summation W2j xj. So j equal to again 1 to 2. Then I have got Z1, then Z2, then summation W3j xj, j equals 1 to 2, I think j equals 1 to 2, and then let us have I. What happened? Any doubt? What? Huh?
Should be W3J ZJ, right?
Oh, correct. Yeah, you are right. W3J. W3J, okay, what are we calling the outputs? Right? I haven't even called them as whatever, yeah. I think I have to call them as certain inputs. So I think let's call this as Z1. Yeah, you're right. I mean, I missed that Z1 and Z2. Yeah, you're right. W3J, ZJ. J going from 1 to 2, and then Y, which is let's say Z3. Let's call this Z1, Z2, Z3, Y is Z3. Okay. So now, right, if I had my x1 and x2 as 0, right, I mean you have 0, 0, 0, 1, 1, 0, 1, 1, right. So if I had it as 0, 0, then what will be right, this summation that goes inside the first neuron. So W1J, so W11 is what, 2, right. So basically 2 anyway, right. So it's all going to be 0. X1 and x2 are both 0, and therefore this is just 0. What about right? No, W okay, that will also be 0. And then what will be your Z1 and Z2? All 0, right? Because your theta 1 is all like is all more than 0. It's all triple. And this one positive. Therefore, Z1 Z2 0. Therefore, W3J, that summation is also 0. And therefore, your Y, right, which needs to exceed. So to get a Y equal to 1, you need the sum to exceed theta 3, and theta 3 is greater than 0. Therefore, the output is 0, which is okay. That's what we want for 0 0. Now, if you put 0 1, right, then what will happen? W11 has no role, but then W12, what is that? Minus 1. Huh? So minus 1 into 1, so that's actually minus 1, and minus 1 is being compared with theta 1, that is 1.5. Therefore, what will be the output? So anyway, right. So I think here let's just write the number, right. So it's minus 1. What about W2J XJ? Minus 1 into W21 is minus 1, and hey, what happened? Did I miss something? W22 I haven't written. Oh no, W22 is 2, no? Okay. So right, W21 is minus 1 into 0, that's 0, and then W22, right, is actually 2 into x2, that is 2, right. Therefore, the second guy is 2. Therefore, what do you think will your Z1 be? Z1 will be 0, but Z2, right, you have to compare 2 with theta 2, right, and theta 2 is 1.5, it's greater than, and therefore, this will become 1, right. Then what will happen here? W3J XJ, right. So W31, oh, I haven't told what W31 and W32 are. Okay, W31 is actually 2 and W32 is also 2. Okay, that's what I've taken here. So then what will happen? So 2 into 0, it's gone, and the other one is 2 into 1, that's 2, right, and therefore this sums up to 2, and then this you have to compare with theta 3, that's 1, therefore the output is 1, right, which is what you want. And similarly 1 0 can right, somebody quickly tell, or else I'll just fill this up, right, let's not waste time. So 1 0, you can just go back and check 2 minus 1, 1 0, right, and then 2 1, okay, and then for 1 1 you get, okay, so 1 1, right, what do you get? You have, I'll write down directly, okay, 1 1 0 0 0 0. Okay, you can actually check this out. So the point is, right, so now, okay, you seem to have been able to get the output, right, that you wanted. This is what you wanted for an XOR, right. Now you can also graphically visualize what's going on. So what we'll do is, we'll actually look at this again. Let's go back to what we had. So we said this, and then we had this and this, right, as 1. The crosses are 1s, the circles are 0 labels, right, and let us kind of, right, look at this guy W11 x1. So W11 is what, 2 x1 plus this is W12, right, for the first neuron, W12 x2. So that is minus x2 is equal to, let's say, theta 1. So theta 1 is 1.5, right, and then the second equation will be W21 x1. So W21 is minus 1, so minus 1, so it's minus x1 plus W22 x2, right. So plus 2 x2, it is equal to theta 2, and theta 2 is 1.5. Okay, this is what you get, or 2 x1 is equal to x2 plus 1.5, and 2 x2 is equal to x1 plus 1.5, right. So let's say that let's find out, right, what is this line. Okay, so what is it? So if I put x2 is equal to 0, I get x1 is equal to 0.75. Yeah, so at some point here, and then if I put x1 as 0, then x2 is minus 1 point, correct, minus 1.5, right? So then it means that, right, it's somewhere here. And okay, right, I'm not drawing it exactly, but then, right, think about it as some line like that. And for the other one, right, you have another line, so which is like if I put x1 is equal to, okay, x2 is equal to 0, x1 is minus 1.5, so it's somewhere here, right? And if I put x1 is equal to 0, then x2 is 0.75, right? So it means that it's somewhere here, because this top cross is what is it, 0, 1, right? So the other line, right, and I think they actually meet or something, right? Okay, they're parallel. Okay. Okay, so the point is this, right? So what you now find is, right, with two lines. Okay, now instead of the earlier one, right, where you had only one line, right? Now you have actually two lines now, and you can kind of, right, and which is what has enabled you to solve the, right, XOR problem now. Okay, so the way to think about it is, whatever is lying between the lines is one class, and whatever is outside this area, right, which outside this region that's being covered by the two lines, right, whatever is outside is the other label. Okay, now this right, along with this came actually, a result that actually said that if you, I mean, here right, for the simple XOR problem. Yeah, one more thing, right, there is just one more thing, right, that maybe I should just mention in passing, is that if you had constrained this neuron to be linear, right, in the sense that right, I mean, this for example, right, I mean, if you did not have a nonlinearity in this theta 1 and say, right, theta 2, then you can show that, right, effectively. I'll just leave that to you as a homework, right, then you can effectively show that the whole thing becomes like a one neuron stuff. Okay, so the idea is that without these nonlinearities coming, this nonlinearity, by which I mean this kind of an activation or a step, right, that you have, which is what is introducing a nonlinearity. If you did not have it, right, you would not be able to solve this, right. If you simply thought that, I can just have something linear out there, which means that, right, you don't have this kind of an activation, simply have some weighted sum there, and then you simply have a weighted sum, okay, under the second neuron, but do not have a nonlinear activation, then you can show that the whole thing will then boil down to doing just this equivalent to just having one neuron out there, which means that you won't be able to solve this problem. Okay, so this nonlinearity is very important. Okay, that is what actually lends you the strength to be able to do the classification, and when they come together in a certain way, like in this case, right, you brought in another hidden layer in between, and you introduced a few neurons, and that is what actually helped you solve the problem. And well, I mean, there are other offset. There are, see, right, this is not the only way to do this, by the way. Okay, you can also do it in other ways, but what I showed you is just one way to do it. Okay, there's nothing unique about this. Okay, this is just to give a window into what's going on. Okay, okay, and then the idea is that, okay, yeah, right. So let me just talk about this. There is a theorem, right, that actually that is for a Boolean function, and then I think then we will go on to. I mean, so which just says, right, what kind of a power, right, this kind of a representation has. So this theorem, right, what it says is that any this one Boolean function, and later, right, we'll talk about real valued functions and so on. Any Boolean function of n inputs, can be represented exactly by a network of perceptrons. So what you saw was something like a very simple network, right, just now, the perceptrons. So perceptrons containing one hidden layer. Okay, we will not actually enter into the proof of all this. Right, this is supposed to be a quick review, right. So one hidden layer with 2 power n perceptrons, and output layer containing one distant perceptron, and output layer containing one perceptron. Of course, but then the thing to note is that this is a sufficient condition. Okay, in the earlier case, right, we didn't require, for example, we had 2 inputs, right. So you would think that in the hidden layer I should have had 4 neurons, right. How did I do it with 2? So this is only a sufficient condition. Okay, and you can actually do with fewer neurons, and the whole strength is that you can actually do it with let's say much less neurons. Okay, this is like the upper limit. Okay, and the real strength of these networks comes because of the fact that you don't really have to satisfy this. Okay, you can do with far fewer neurons and still be able to accomplish what you want, like we did for that small example, right. We used only 2. Now, right, I mean, otherwise the whole thing will just, right, explode, right, exponentially.